In this video, we'll talk about how antiderivatives relate to the equations of motion. Now, we want to be able to answer a question like the one you see here. Suppose an object falls from 400 feet. How long does it take to hit the ground? So in this problem, we have some object which is suspended 400 feet above the ground, and then it simply falls under no force other than gravity, and we want to know how long it takes to hit the ground based on that information alone. What are we trying to do here? We want to find how long it takes to hit the ground, so we need to know some way of describing its position relative to the ground. And for that we need what we call the position function. So let's start by letting s of t be equal to the distance above the ground after t seconds. So this is what we call the position function. And what we would really like to know is a formula that gives us the position function describing the object in this problem. What do we know about the position function right now? Well, we know that it starts 400 feet above ground. So we know at this point that s at 0, so after 0 seconds, is 400 feet. What we would like to know, so we want to know, s of t is equal to 0 for what value of t? That's what we really want to know. We want to find some value of t where the distance above ground, which is st, is going to be 0. Now, in order to do that, we want to determine a formula for the position function s of t. How can we do that? Well, we do that based on the information given to us. And actually, there's something else that we need to know that isn't listed here. So we need to know one other thing, which is that the acceleration due to gravity, is approximately 32 feet per second, or feet per second squared if you prefer. It's also approximately 9.8 meters per second squared. In this particular problem, we're dealing with feet, so we're going to use the 32 feet per second squared. All right, so gravity is the only force acting on this object, so what we know is that the acceleration due to gravity is 32 feet per second squared downward. So that means we're going to have a negative sign at some point. So we know that the acceleration, so if we let a of t be the acceleration, after t seconds, then a of t is a constant minus 32 feet per second squared. Minus because it's going down. All right, well, in order to get from a to s, we need to recall what the relationship is between the position function and the acceleration function. So recall that s prime of t, what is that going to give us? That's going to give us the rate of change in position over time, which is going to give us the velocity. The velocity after t seconds. And if we differentiate that again, s prime prime of t, the second derivative of the position function, that's the first derivative of velocity, and now we're measuring the rate at which the velocity changes over time, and that's the acceleration. So the acceleration is the second derivative of the position function. And it's the position function that we want to know. We don't know that, but we do know the acceleration. So we know not the first derivative, but the second derivative. So we just need to move up first from the second derivative to the first derivative, and then from the first derivative to the zeroth derivative, or the position function. So how's that going to work? Well, again, we know that a of t is equal to minus 32. Now, a of t is the derivative of velocity. So that tells us that velocity prime is equal to negative 32. So if we want to find v, or the velocity, we need the antiderivative of negative 32. Well, that's just simply a constant. So v at t is equal to minus 32t. Well, plus some constant, some arbitrary constant. Well, it's a specific constant. We just don't know what it is yet. In order to identify the value of c, which we need to do, we need to find the value of c. We need an initial condition. Well, what initial condition do we have for the velocity? Well, nothing is explicitly stated, but if you look back at the statement of the problem, we know that we have an object which is suspended 400 feet above the ground, and suddenly it's released. That means there is no initial velocity imparted to the object. It's just sitting there. So what that tells us is that v of 0 is equal to 0. It has no initial velocity. It's just sitting there. Well, that makes it very easy for us to identify the value of c, because we know that when t is equal to 0, v of t is equal to 0. So that means we can just plug in v of t equals 0 is going to be minus 32 times 0 plus c. Of course, minus 32 times 0 is 0, so you just end up with c. But we know that v of 0 is equal to 0, so that tells us that c is equal to 0. So that tells us what our velocity is. v of t is equal to minus 32t. Okay, that's good. But now where do we go from here? Well, velocity is the derivative of position. So s prime of t is equal to minus 32t. And we need to find the antiderivative. So s of t is the antiderivative of this power function, well, minus 32 times a power function. So we increase the exponent by 1, and we divide by that new exponent. And then we need to add in some sort of constant. Now this c is not the same as the other c. This c was a constant, and this c is another constant, but they're not the same. So this is our constant, and we need to find the value of c. We need to find the value of this c. Okay. Now notice, of course, we can simplify our position function a little bit. S of t is equal to minus 16t squared plus some constant. Now, in order to figure out what that constant is, we need our initial condition. And what is our initial condition in this case? Well, it's the initial position, which we know that s of 0 is 400. All right, so now we can just plug that into here. So s of 0 is minus 16 times 0 squared plus a constant. And of course, minus 16 times 0 squared is 0, so you just end up with c. So we have s of 0 is c, but we know that s of 0 is 400, so c is equal to 400. This gives us the position function. S of t is equal to minus 16t squared plus our constant, which is 400. All right, that gives us our position function. Well, what we're looking for, what we want, recall, we want find t so that s of t is equal to 0. Well, this is now a matter of solving an equation, a quadratic equation, in fact, because we know that s of t is minus 16t squared plus 400, and we want this to equal 0. We need to solve for t in this case. The first thing we can do is we can get that minus 400, or get that 400 on the other side, and it becomes a minus 400. Minus 16t squared is equal to minus 400. Now divide both sides by minus 1, and you have 16t squared is equal to 400. So t squared is equal to 400 divided by 16, which is 25. So what does that tell us? That tells us that t squared is 25, so t is equal to 5, or t is equal to negative 5. Now, we can't have negative time, so we rule that one out, and that just gives us t equals 5. So that tells us that 5 seconds after it's dropped, the object hits the ground. And that's the answer. So let's write it out in words. It takes 5 seconds to hit the ground. So this is an example of solving a differential equation with not a first derivative, but with a second derivative. Now notice, in order to do this, we needed two initial conditions. We needed two initial conditions. We needed to know that v of 0 was equal to 0, and we needed that s of 0 was equal to 400. So if you start with a differential equation that has a second derivative, in order to solve that differential equation, you're going to need two initial conditions. Let's do another example, just for fun. Suppose an object moves with non-constant acceleration. Let's say the acceleration is given by the formula a of t equals 2t plus sine of t, whatever object this happens to be. Our goal is to find the position function, so I'll need two initial conditions. So we're supposing an object moves with this acceleration, and suppose the initial velocity is v of 0 equals 1, and initial position is, let's say, s of 0 is equal to 3. Okay. So our goal here is to find a formula s of t. That's our goal. Now, I want to just make one comment here, which is the terms, initial. You can see here where this term comes from. We're looking at v of 0 is equal to 1. That's the starting value. And we're also looking at s of 0 equals 3. That's the starting value, or the initial value. This is where these terms come from, because very often the initial velocity, initial position are what the starting values are. Now, they don't always have to be v at 0 and s of 0. You just need some value of t to be known, v of t and s of t for some t. But in this case, and very often, that initial value is 0 when it's starting. All right, so let's solve this problem. We have the acceleration. Acceleration at time t is 2t plus sine of t. Now remember that acceleration is the first derivative of velocity. So if I want to find the velocity, I simply have to find the antiderivative of 2t plus sine of t. Well, 2t, we know, it's 2 times, and then you increase the exponent by 1 and divide by that new exponent. And now what about sine? Well, the derivative of sine is cosine, but the antiderivative is negative cosine plus some constant. Right? Let's simplify this. V of t is equal to t squared minus cosine of t plus a constant. Now, before we proceed, we want to identify what the value of that constant is. And for that, we're going to use our initial condition, v of 0 is equal to 1. So we just simply plug in t equals 0 to see what happens. V of 0 is equal to 0 squared minus cosine of 0 plus c. Okay, well 0 squared, of course, is 0, but cosine of 0 is 1. So that tells us that we have minus 1 plus c, and that's equal to 1. So c is equal to 2. So c is equal to 2 in this case. So now we know that the velocity at time t is equal to t squared minus cosine of t plus c, but c is equal to 2. Plus 2. That gives us the velocity, and now we remind ourselves that velocity is equal to the derivative of the position function. All right, so that means if we want to find s, we need an antiderivative of v. And again, we use our power rule. We increase the power by 1, it becomes a 3, and then we divide by that new exponent. And now we have minus the antiderivative, or an antiderivative, of cosine, which is sine. Derivative of sine is cosine. Plus, here we have a constant, the antiderivative of 2 is 2 times t, and now we just add a constant to it. All right. Now again, this constant plus c is not the same as the original plus c. I'm just using c as an arbitrary constant, but we need to figure out what the value of that constant is, and again for that we resort to our initial condition, s of 0 is equal to, in this case, 3. All right, so let's just compute that. You plug in t equals 3 and you end up with 3 cubed over 3, which is 9, minus sine of, no, it's not sine s of 3, it's t is equal to 0 in this case, t is equal to 0. So s of 0 is equal to 0 cubed over 3, which is even easier to compute, that's 0, minus sine of 0 plus 2 times 0 plus c, and this is equal to 3. That's where the 3 comes in. But notice all of these things are just 0. So you end up with c is equal to 3, and that gives you your position function, s of t. So s of t is equal to t cubed over 3 minus sine of t plus 2t plus our constant, which is 3. And that gives us our position function.